the last lecture, we learnt that metals have free electrons, and these free electrons can move in response to an electric field. However, we also learnt that the drift speed of these electrons is very small. So, how is it that a meaningful current gets established? Let me give you an example. Suppose you are standing on a roadside at some point, and there are large number of people going in one direction. Although they move with very small speed, a large number of people will get across the point where you are standing. So, a large current in the case of electrons can be established. We also learned that when resistances are in series, they get added up. When the resistances are in parallel, then the reciprocals get added up. Now, in this lecture, I shall continue from that point, the parallel and series combination of resistances. I have chosen this example to illustrate. You see, at the point C, part of the current goes to A and part of the current goes through B. At B, there is no such division of current, and all that current that comes to B goes to A. So, these two resistances are in series, while they are in parallel with the resistance in the arm C A. If I redraw the circuit, then this will be like this. These two resistances are this here, and this point B is here, and these two are in series, and this combination is in parallel with this. Let us take another example. Consider a circuit which have these 5 resistances, and they are, you see, these two are in series, they are in parallel with this. So, these two are in series, 10 plus 20 is 30, they are in parallel with 60. Therefore, 1 by 30 by 1 by 60 gives 20. So, there is this resistance is 20, this is also 20, they are in series. So, they make the resistance 40. So, if I redraw the circuit, this resistance is 40, this resistance is 60. So, now they are in parallel. So, 1 by 40 plus 1 by 60, and the reciprocal of that is just 24. So, these 5 resistances, their effective resistance or the equivalent resistance is just 24 ohms. That is how we proceed with the resistances in series and parallels. Like we did for the capacities, let us also do it for the resistances. We have an infinite network, and since the network is infinite, I can take this element out, and then the rest will still remain infinite. Suppose the equivalent resistance of the rest is just R. Then if I redraw the circuit, I get this is R. So, this is R, this is in parallel with 6, and then 3 and 5 are here. So, I will find the effective resistance of these two parallel resistances, which is 1 by 6 plus 1 by R, reciprocal of that, which is 6 R by 6 plus R. So, they are now in series. So, 5 plus 3 plus 6 R by 6 plus R, and their value must be equal to the value for the infinite network equal to R. So, this is a quadratic equation which we can solve. This has two roots, 12 and minus 4. Minus, of course, is unphysical because resistance cannot be negative. So, we have the resistance of this network equal to 12 ohms. Sometimes you will get sort of confusing thing like this. The examiner will ask, what is the effective resistance between points A and B? If you just think a bit, you can redraw this circuit. This resistance, and this resistance, they are in series, and these 3 are in parallel with this. So, they are 4 plus 4 plus 4 12. So, 1 by 12 plus 1 by 4, and the reciprocal of that is just 3 ohms. So, the combined resistance between points A and B, or the effective resistance between points A and B, is just 3 ohms. Another very complicated looking network, but it is not really complicated. Each cell of this network is actually 2 resistances in series, 2 here in series, and then they are in parallel with this. So, this series is in parallel with this, and this series is in parallel with this, and we can find out this is 4 plus 4 8, This is also 4 plus 4 8, this is 4. So, we have 1 by 8 plus 1 by 8 plus 1 by 4 and that adds only to 2 ohms. So, each of these cells has resistance 2 ohms and there are 4 of such. Therefore, the total resistance between A and B is 8 ohms. Another example, when a wire of uniform cross section A and length L and resistance R is bent into a complete circle, what will be the resistance between any two diametrically opposite points? So, these are diametrically opposite points. So, what happens in this? Then this half circle resistance and this half circular resistance, they are in parallel. The total resistance is R, therefore, half of this is R by 2, this resistance is also R by 2. So, two resistances each R by 2, they are in parallel. So, therefore, the net resistance is 2 by R plus 2 by R raised to power minus 1, which is R by 4. So, the net resistance of this circuit between these 2 points is R by 4. A wire of certain material is stretched slowly by 10%. So, I have a wire, I stretch it slowly by 10%. That is, if its length was 10 centimeter, it becomes 11 centimeters. Find its new resistance and specific resistance. Now, here the examiner is trying to confuse you. Specific resistance does not change. I told you in the last lecture that specific resistance is the property of the material, does not depend upon length or area of cross section. So, that does not change. So, one part is over. The second is the new resistance. Now, if the length is increased and if nothing else changes, then the volume must remain constant. So, therefore, if the length is increased, the area of cross section must change. That means, earlier length was L1 and earlier cross section was A1, then L1 A1 must remain equal to L2 by A2. That means, the new cross section is L1 A1 by L2 and the resistance is, say, the new resistance R2 is rho times, rho is the resistivity, L2 by A2. So, I substitute A2 from here and I can write it like this. This is L2 square by L1 square into the old resistance, which is rho L1 by A1. Therefore, the resistance increases by this factor L2 square by L1 square and L2 by L1 is 1.1, 10%, and therefore, the new resistance is square of that, that is 1.21 times the old one. Let us now introduce this new term electromotive force or EMF and distinguish it from the potential difference between 2 points, 2 terminals of the battery. As the name suggests, electromotive, that means it is something that makes the charges move. And what are the sources of EMF? Voltaic cells, for example, Leclanche cell or the other cells that you have learned, solar cells, electrical generators and varying magnetic field. We will learn later that when magnetic field varies, EMF is produced. Formally, EMF is defined as the energy provided by a cell by chemical reactions or any other device, for example, changing magnetic fields. And if the energy is dW and the charge pushed is dQ, then the EMF is defined as energy per unit charge dW by dQ. And if the work done is in joules and the charge is in coulombs, then the EMF is in volts. The EMF is measured in volts and is equal to the potential difference across the terminals of the cell on open circuit, that is, there is no current flowing through the circuit, open, the key is open when no current is flowing. If at that time we take the potential difference across the 2 terminals of the battery, then it is an open circuit and it is equal to the EMF. When the circuit is closed, then the current starts flowing. I have closed the key, therefore, the current starts flowing and every cell has some internal resistance. In addition, we have also the external resistance R. Therefore, the EMF, therefore, which is pushing the charge is equal to the current into R plus R. And IR is, what is IR? IR is nothing but the potential difference across the terminals of the battery. Therefore, since IR is V, I can write V equal to epsilon or the EMF minus I times R. In fact, you can see I times R is the work done in overcoming the internal resistance of the cell. That reduces the EMF by amount IR and the result is the potential difference across the terminals of the battery. And if I plot V against I, then you will have this curve. This is the offset epsilon, and the slope of this curve is a straight line, and the slope of this curve is minus r. You can compare with y equal to m x plus c, and you can see the slope is minus r. Now, each application requires a certain voltage to run it. At the same time, we also have to think of the capacity of the battery used in the application. The capacity of a battery is the amount of charge it can supply at a specified terminal voltage, that the voltage does not come down from this specified voltage as the battery is supplying the charge. Since charge is current into time, the capacity is measured in ampere hours, capital A times H. For example, at your home, a typical inverter battery, if you look at it carefully, will state that the capacity of this battery is 135 ampere hours. It can be 150, it can be 100, but generally the capacity of such batteries is 135 ampere hours. This means that this battery can supply 1 ampere for 135 hours without reducing the voltage of the battery beyond a certain point. If I specify a certain level, then it can supply current up, so that the voltage remains above that level, and it can supply 1 ampere can be supplied for 135 hours. If I draw only half an ampere, this will be 270 hours, and like that. You must have read in chemistry that the potential difference that develops across a cell is a function of the chemical reaction. All cells having the same chemical reaction develop the same potential difference, the same voltage. For example, your familiar AA batteries, they have the potential difference 1.5. The smaller AAA batteries, they also have potential difference 1.5, because both of them have the same chemical reaction, which is based on the Lagrange cell, based on the reaction, and therefore, they produce the same voltage. All lead acid cells, the kinds that you use in inverter battery or in a car battery, they develop a voltage of 2 volts, because the reaction in them is the same. All nickel cadmium cells develop a voltage of 1.2 volts. The capacity of a cell, on the other hand, is determined by the amount of time the chemical reactions last. That means, the amount of material inside the cell, that means the size of the cell. So, the size of the cell determines the capacity, whereas the reaction of the cell, reaction inside the cell determines the voltage. So, coming again to the example of AA and AAA type, AA are thicker, they have more material in them, reactions can last for a longer time, therefore, they have larger capacity than the AAA, which are thin cells. So, let us now return to the grouping of cells. We connect them like this, the positive of this connected to the negative of the other, and then the negative of the next connected to the positive of the other, and so on. So, these are the connections in series, and each of these has internal resistance R. Therefore, the total internal resistance is N times R. These are in series again, and there is an external resistance R. The potential difference from this point to this point, because of n cells in series, is simply N times E, N times the EMF. Therefore, the current that we can draw is N times epsilon voltage by resistance R plus N R. And if N R is much smaller than R, then I can neglect this, and I will get I equal to N epsilon by R, N times EMF by R. EMF by R is the current due to one cell. So, if I have n cells in series, then the current becomes n times the current that we get from one cell. That is, if the internal resistance is small compared with the external resistance. If the external resistance is small, that is, I can neglect this, then I is simply equal to N times epsilon divided by N times R, and gets cancelled. It is the same thing as if we are taking the current through a single cell. Parallel grouping. In parallel grouping, all the negative terminals are combined to one point, all the positive terminals are combined to another point, as in this, and then the current is drawn through the external resistance R. So, what do we have? external resistance R, internal resistance is parallel. So, if one resistance is small r, then this will be R by N, and total resistance is therefore R plus R by M. N we use for the series combination and M I am using for the parallel combination. So, therefore, the current now is the voltage, whether you take here, here, here or here is the same, because they are all in parallel, and therefore, the current is the EMF of one cell divided by R plus R by M. R by M is the total resistance of this, all the resistances are in parallel, therefore, the resistance is R by M, and therefore, I can write this as M times EMF of one cell divided by MR plus R. So, once again I can take the same special cases. If the external resistance is very large, then I can neglect R, and then the current will be as if through one cell, and if external resistance is small, then the effect of the parallel combination would be that the current will be M times the number of cells times the current through one cell. Usually, we have actually a combination which has series and parallels. So, I have in one row there are n cells and there are m such rows. This is a combination which consists of both parallel and series combination. This is called mixed grouping or mixed combination. So, in this case what happens? In one row the resistance is n times R, there are m rows, therefore, the total resistance is n R by M, n R by M. R is the external resistance and the potential difference is equal to n times the EMF across each cell, because there are n cells in each row. So, therefore, the current is n times E, the voltage, divided by R, which is the external resistance, plus n R by M. One can write this as M n epsilon by M R plus n R. Now, what is the advantage of these? First of all, of course, we can maximize the current if we minimize the denominator, and this can be done if we write the denominator as this, square of this plus this. So, if I make this equal to 0, then the current is maximized, and that means M R must be equal to N R. If M R is equal to N R, remember N is the number of cells in each row, they are in series, and there are m such rows. So, if R is equal to N R by M, then we get the maximum current. Mixed grouping is often used to get not only the desired voltage, but also to boost capacity for longevity of the battery. If you use laptops, then if you see the battery that it uses, you will find that laptop batteries have 4 cells, each of 3.6 volts, providing 14.4 volts for its operation in a row, and then there are 2 rows to boost the capacity, so that the battery lasts for a longer time. You can work with the laptop for a longer time. Let us take an example to clarify these ideas. Here there are 2 cells, each has the same EMF, but resistances are different, R1 and R2, and R1 is greater than R2, and this is the external resistance. And what it says is, when the circuit is closed, the potential difference across the first cell is 0. Find the value of R. So, see this circuit, we have R1, R2, they are in series and they are parallel to R. So, the current therefore is, and there are 2 cells of EMF E, therefore, the current is 2 EMF, 2 times the EMF divided by R plus R1 plus R. And now, the condition given is that the potential difference across the first cell is 0. So, the potential difference across the first cell we have seen is I R1 minus epsilon, V we have seen is I R minus epsilon. So, from the first cell we get I R1 minus epsilon is equal to 0, from this we get epsilon. So, we will substitute epsilon here, the EMF, and then we get I gets cancelled, and we have an equation in R, small r 1 and small r 2, and we can solve, we can see that the external resistance must be equal to R 1 minus R 2. You must have seen solar panels at various places. Here I have chosen 3 solar panels and they are connected in a certain manner. I want you to recognize this, the way in which they are connected. Can you recognize that they are connected in parallel? these combinations in parallel? If not, then notice this, plus of this panel goes to the plus of this panel also goes to the plus of this. So, all 3 plus terminals, positive terminals are connected at one place, all 3 negative terminals are connected at one place. So, therefore, these panels are in parallel. These are in parallel. Why are they in parallel? To just boost the capacity. Notice that all positive terminals are connected at one point and all negative terminals are connected at one point. All positive here, all negative here. Each panel develops a voltage of 12 volts and gives a current of 4 amperes. The internal resistance of the panels is generally negligible, it is very small. So, the maximum current given by the panel is M n epsilon by M r plus N r, the formula that we derived earlier for the mixed grouping, and this reduces to, because since the internal resistance is very small, this comes out to be N times the EMF of one panel divided by R, and this is equal to 12 amperes. Because each gives 4 amperes, 3 of those 3 times this will give you 12 amperes. The voltage of parallel combination remains 12 volts. The voltage remains 12 volts because they are all in parallel. So, the voltage between these 2 points is just 12 volts, but the capacity goes up because we have 3 in parallel. Therefore, the capacity goes up. Can you recognize this? Again, you see in each column there are 2 batteries or 2 devices which are joined in series. These 2 are joined in series, these 2 are joined in series, these 2 are joined in series, and then the positives of these are connected at one point and negatives of these are connected at another point. So, what do we have? We have again a mixed combination, 3 columns, each 2 batteries or devices in series and 3 such combinations in parallel. So, what is the total output? Total output will be the output of each column. Each column is 6 volts plus 6 volts 12. So, the output of this is 12 volts, this is 12 volts, this is 12 volts, and they are all connected in parallel. Therefore, the total output is also 12 volts. However, the capacity, it was 100 ampere hours, 100 ampere hours, 100 ampere hours here. You see, 2 cells in parallel or 3 cells in parallel is all like making a very big cell. And I told you that the capacity of a cell depends on the total material available, and therefore, the capacity of these combination is 100 plus 100 plus 100, that is 300 ampere hours. So, in this lecture we have focused our attention on the combination of first the resistances, then the combination of cells. We also highlighted the capacity of a cell. Capacity of a cell depends upon the total material available for producing energy inside the cell, whereas the potential difference of a cell depends on the chemical reaction that goes on inside the cell. That is all. That is why all dry cells that we use daily, AA or A type, they have the same voltage 1.5, and all batteries used in inverters or in cars, they have, each one of them has voltage 2 volts because of again the chemical reaction then it goes on. But when we add such things in parallel, then it is as if we are adding the material in them, and therefore, the capacity in a parallel combination, the capacity gets boosted. In the next lecture, we shall take up the question of finding resistances, currents and voltages in various arms of a given complicated circuit. We shall enunciate the Kirchhoff's laws and then use them to find out the resistances or currents or voltages in the various parts of a complicated circuit.